We now begin a new topic on cell balancing, and as a introduction to this topic, I ask you to realize that we've now explored all of the basic estimation tasks that are performed by a battery management system. We've estimated the state of charge, as we've seen. We've estimated the state of health of a battery. In other words, the state of a battery model and the parameters of a battery model. And now we're looking at some of the more control-oriented tasks required by the battery management system. So the first one we look at is the focus of this chapter, which is on balancing or equalizing a battery pack. And then in the remainder of the course, we'll be looking at computing power limits, which is also really a control task more than it is a basic estimation task. So just as a reminder, this graphic here shows us the progress of the course, where we started out by looking at measuring all of the very primitive quantities of voltage and current and temperature, and then using those together with a model of battery cell dynamics to estimate this internal state. And now we've just completed a section on estimating the parameters of that model also. All of that looks inside the cell. Balancing cells now begins to look at things from more of a pack level of cell-to-cell variations, and so will the power limits when we get to those chapters. Balancing, what is it, you might ask? Well, balancing a battery pack or equalizing a battery pack is the process of modifying the level of charge in the cells of a battery pack on a cell-by-cell basis. And so understand that if I have a series connected battery pack, whatever current goes through the pack, exactly that current goes through every one of the cells because of Kirchhoff's current law. And even if I have cells connected in parallel to make some kind of modules of cells, through any one of those parallel combinations, the total current has to equal the pack current. And I'm not really doing anything intentionally differentially between the cells. So balancing is somehow finding a way to make more current go through some cells than through others, so that we can modify the level of charge in some cells versus the level of charge in others. In this section right now, we're going to look at causes of imbalance, so why we would need to do this, but also some things that are commonly thought by people new to the field to be causes of imbalance that really are not, just so that you have a very clear picture of that. We're going to look at two basic approaches to balancing. One of them is passive balancing, and passive balancing simply drains charge from cells that have too much charge in them, and the dissipated energy is drained as heat. And we have to make an active choice to do passive balancing because we have to turn on circuitry that does the balancing. But the term passive, I believe, refers to the fact that we are not actively moving energy around in that sense, but we are passively dissipating energy as heat. Active balancing, on the other hand, is trying to take advantage of the energy that we already have and to move charge from cells that have too much into cells that have too little charge, so that we attempt to conserve energy in the battery pack and not simply remove it as heat, as does the passive balancing method. We're going to look at some balancing circuits and some balancing strategies and some balancing thoughts, but we start out by considering why balancing is important. And we return to this simple battery pack that we've seen a number of times already, and you're probably tired of analyzing this battery pack. But remember that when I've got one cell that is at 0% state of charge and one that is at 100% state of charge, that battery pack is not useful. If I try to use the battery pack to deliver energy to a load, I will over discharge that cell on the top. Or if I try to charge the battery pack, I will overcharge the cell that's on the bottom. So this battery pack cannot deliver charge or power or energy. It can't accept it. So this pack is useless, even though the cells might still be healthy cells. So this is a battery pack that we would call out of balance. There's different definitions of balance, and we'll talk more about that. But at least for now, we could think of the state of charge of the cells not being the same as an indicator that this pack might be out of balance. And these cells have states of charge that are very, very different from each other, which is causing the pack to be useless. So to balance this pack, we would either individually drain charge from this cell by putting some kind of a resistive load in parallel with that cell, and then that would bring this cell down to 0%. We've wasted energy as heat, but we've brought the pack into a configuration where now both cells are at 0% state of charge, and now I can charge the battery pack normally and bring both cells up to 100% state of charge. That would be the idea there with passive balancing. With active balancing, somehow we would have circuitry that would move charge from that cell to that cell, and if the circuitry was 100% efficient and everything else was matched, we would then have two cells that were both at 50% state of charge. And then I could continue and charge the battery pack using the external source, or I could discharge the battery pack. And the point with the active balancing is that I'm not wasting all of the energy that's stored in this cell as heat. I'm actually recovering that energy. And in an actual circuit, it would not be 100% efficient, but I could recover a lot of that energy from that cell. So generally, why does this happen? Well, we're going to talk about that, but in some sense, we talk about there being a weak cell in the battery pack and a strong cell, maybe. And it's the weak cell that is somehow going to limit the pack's performance, and ultimately, over time, it will make the pack useless unless we actually do this balancing. So this chart here is a cartoon, really. It's not a real thing. It's more of showing an idea where on the vertical axis we plot state of charge, and this is the maximum allowed state of charge, and this is the minimum allowed state of charge in the application. And at the beginning of time, the good cell and the weak cell both have the same state of charge, but as I discharge the battery pack, the weak cell somehow discharges more quickly than does the good cell, and as I charge it, again, the good cell charges more quickly than the weak cell, and so forth. And you see that over time there's a divergence between their states of charge. It never converges back normally, under normal circumstances, that is. And so over time, you can imagine if we operate a battery pack that has that kind of a dynamic, that you will get this scenario here. And it reminds me of a story I heard of what happened during the Beijing Olympics, where Beijing or China had developed electric buses to bring all the athletes around the Olympic Village, and kind of as a statement of, hey, we are progressive here, we want to have electric powered vehicles and so forth. Except that they didn't have balancing circuitry built in. And over the course of the Olympics, which, the actual events aren't very long, but the athletes come in earlier and they train and so forth. Over the course of the Olympics, the range of these buses dropped by about 50%, is the story that I hear. So even over a relatively short amount of time, it's possible for battery packs to become very imbalanced. So you can imagine purchasing an electric vehicle for a lot of money and you're very proud of it. But after a couple of months, if you have only half the range, that would be awful, especially because all the cells are still perfectly healthy. So we need to do this balancing. We need to be able to keep all of the cells more or less together in terms of state of charge versus time or some other performance variable versus time. Let's look a little bit at why a battery pack might become imbalanced in terms of quantities that we're already familiar with. And we'll think of imbalance in terms of state of charge of the cells being different from one another. So one example is when cells have different coulombic efficiency. Let's look at this equation here. This is the state of charge equation, and we've learned that it's not a very useful equation by itself to use for estimating state of charge, but it actually does accurately describe state of charge. It's not too useful because it's hard to know the quantities in it accurately enough to use it without feedback, but in fact, if we did know the quantities, it would describe it perfectly. So looking at this equation, we'll look at coulombic efficiency first. And remember that coulombic efficiency we're saying is 1 for all cells when I'm discharging, but any time that I'm charging the cell, the coulombic efficiency is not 1, and it may be different for different cells. And so again, I have kind of a cartoon-like picture here to indicate what might happen. We have state of charge on one axis and time on the horizontal axis. And in this picture, both cells start out at the limiting low state of charge. And then a good cell has a high coulombic efficiency, so as I put current into the battery pack, it will utilize all of that current, or the vast majority of that current, to affect a change in state of charge, and so we see that there. And it reaches the upper state of charge limit before the other cell does. This one has a lower coulombic efficiency, so there's some side reaction or something going on where not all the pack current contributes to charging the cell. And at the end of this charging interval, the states of charge are different. And so you can imagine if I were to continue by then discharging, well, both of them have exactly the same coulombic efficiency on discharge. So the distance between these cells remains, that distance and that distance are the same, but next time I charge, the strong cell charges better than that one does, and well, it doesn't last that long, does it now? But then I get a bigger difference, and over time, after a number of cycles, I have a growing divergence between the states of charge of the good cell and the weak cell. So that's one thing that can cause the cells to diverge. Then looking at the equation, another thing to think about is there any way for the net current experienced by different cells to be different? So the net current we write as the applied current to the battery pack, but there's also some self-discharge that may be different from cell to cell, and there's some leakage current. Leakage current I'm thinking of as external to the cell due to the electronics or the wiring, the packaging that the cell lives in inside of the battery pack, whereas self-discharge is something internal to this cell because of some chemical side reaction processes, or maybe a separator between the electrodes that's becoming thin in one cell and is becoming low resistance in some spot, or something like that. But you can see that if there's a lot of leakage and self-discharge on one cell versus another cell, it would have a very similar effect as having a different coulombic efficiency, except it would also operate when the cell was resting, and it would also operate when the cell was discharging. So in fact, it could be more severe than a different coulombic efficiency, depending on how fast the self-discharge happened to be. So I think we said all of that. So here we have a picture of that where both cells start out at the same place, but the good cell has low self-discharge and low leakage, and the poor cell, the weak cell, has a higher self-discharge or a higher leakage current. And so the weak cell hits its low state of charge faster, and we get a divergence at the end of this discharge that would never be normally corrected just by normal operation. So when cells draw a different net current, they're going to become imbalanced. So what about temperature? Well, temperature plays a role because the self-discharge rates and the electronics performance and the coulombic efficiencies are all functions of temperature. So a battery pack that has a temperature gradient, in other words, it has low temperatures in one place and higher temperatures in another place, can make the problem worse because of it. It really amplifies, the temperature difference amplifies a problem that's already existing. But in any case, in all of the cases, it's a difference in efficiency or self-discharge or leakage that matters. It's not the absolute quantity. If I had a coulombic efficiency was set of 0.99 is pretty typical, maybe even higher than that. But if all of my cells in my battery pack had a coulombic efficiency of 0.8, that would be awful, but it would not lead to imbalance if they were all exactly 0.8, because when I'm charging, they would be losing just as much charge equally to each other. So if all cells are equally bad, then there's not going to be an increase in imbalance, even though my battery pack is not operating in a very efficient way. So it's difference that matters, of one cell charging faster than another cell or discharging more quickly than another cell. There are some things that are not causes of imbalance that you might think would be causes of imbalance. There's things that cause a kind of a temporary imbalance that's self-correcting. And if it self-corrects over time, then it's not really something to be worried about quite as much as something that does not self-correct over time. So let's look at a difference in capacity. Suppose I have a battery pack where I have a 6 amp hour cell, that's my strong cell, and a 5 amp hour cell, which is my weak cell. Of course, we would design the battery pack so that the capacities were the same, but over time, one of them has aged more quickly and has a lower capacity. That's the concept here. Let's start both of these battery cells at the same state of charge, and let's remove 5 amp hours. So this here, I have 6 amp hours minus 5 amp hours equals 1 amp hour, so that's the capacity that's left there. And over here, the weak cell, I have 5 amp hours minus 5 amp hours equals 0 amp hours, and that's the capacity there. So you say, that looks like the battery pack is becoming imbalanced. And I agree that it looks that way, but let's see if it is self-correcting. Let's look at the charging. So this is 1 amp hour plus 5 amp hours equals 6 amp hours. Oh, it's full again. And this one here is 0 amp hours plus 5 amp hours equals 5 amp hours. Well, the weak cell is full again too. It's up to its capacity. So if I have battery cells with different capacities, and I discharge the same amount from the cells and I charge the same amount in terms of amp hours, they end up at the same place. So this is a self-correcting capacity imbalance. It's not something that is going to continually diverge over time and cause the battery pack to become useless. This is something that has only a minor impact. The minor impact is that we do limit the available energy. If we examine that point right there, the weak battery cell has no charge left in it, so I cannot take any energy out of the battery pack. However, the strong battery cell still has 1 amp hour of charge left, a 1/6, about 16% state of charge. And so there's energy left in the strong cell that is not possible for me to remove from this battery pack. There's kind of unavailable energy. It's not available because I can't get it out of the pack. So if we have a way of actively balancing the battery pack quickly, passive balancing dissipates energy. So if I use passive balancing, sure, I could make that cell have 0 state of charge at the same time as the weak cell, but I've just wasted all the energy as heat, so I don't get any usefulness out of it. But if I do active balancing, where while I'm discharging, I'm moving some charge from that cell to that cell, it would bring both of them together, so the state of charge would be more equal for the two cells, and I could get more energy out of the battery pack. So if we can do active balancing quickly, it's possible to get more energy out of the battery pack than if I don't do any balancing. But then I'd have to do some balancing on the charge as well in order for both of them to be charged to the same level in the same amount of time. So you can imagine that this is harder to do well, but there are some potential benefits to doing it. So we'll look at active balancing later on in the chapter. So different capacities don't really cause a long-term imbalance in the battery pack. It's a short-term imbalance that self-corrects. Similarly, different cell resistances also don't cause an imbalance. Now, what would happen if we extend these lines, and I start with 2 battery cells, they would both, because if they have the same capacity but different resistances, they would both go down at exactly the same rate. However, the high resistance cell is going to hit a voltage limit before the low resistance cell does, and so we stop discharging before we get to the minimum SOC, because the high resistance cell says, if you try discharging me anymore, I'm going to have an undervoltage condition. And similarly, when you charge, the two curves are going to be the same, but they're going to stop before I get to 100% SOC, or the maximum rated SOC, because the high resistance cell would have too high of a voltage on charge. So having different resistances limits the state of charge range that you can use and still get your acceptable power out of it, but it doesn't cause imbalance. These states of charge of the cells are identical to each other if resistance is the only thing that's different. So a cell with high resistance hits this lower voltage limit before the others, and it limits the power. So here we limited energy by having different capacities. Here we limit power by having different resistances. And again, the fast active balancing can help get more power out of a pack for longer by taking, in this case, the cell that has the higher resistance and biasing it towards a higher state of charge so that it will not hit the voltage limit as quickly, and so that both of these cells would then hit the voltage limit at the same time, and I could get closer then to this design limit. And then similarly, on the charge, when the strong cell is going up like that, we would want the high resistance cell to do something like that in order for it not to hit the voltage limit as quickly. So we would intentionally bias the states of charge of a pack with cells having different resistance if we wanted to get more power out of it, and we could do that with fast active balancing. Again, you can imagine that this is more complicated, but it's certainly doable and might be worth doing in some situations. So that gives you an idea of why a battery pack might become imbalanced over time. Over the next section or so, we're going to look at some design choices that you would have to make when you're designing a balancer. And I'm not really going to give you answers. I'm just going to give you questions and ideas, because the answer depends on the situation and the budget and so forth. So you would have to think about when would I use this solution versus some other solution but I at least want to bring up the questions for you to have available when you're designing your own balancing system.